All right, so let's talk about graphing, and there's some very specific instructions for some of these on the MyLab and on the homework. And that is, we want to use the basic exponential function just to understand what happens when we have not just y equals e to the x or y equals 4 to the x or whatever it is, but you have e to some constant times x, that thing multiplied by something and then plus something else. It's kind of, there are some algebra tricks that you can use in some situations, but we want to understand kind of situations where we have all three of these things at the very least. It's kind of, fairly typical, and we want to sort of review what some of the effects are of these transformations. So that was section 2.5 is transformations, and then what are we starting with? This is our new, this I just got from the calculator, but my instructions are going to say, well, e, we want to get used to using e to the x. So that's just something we're going to have to do. And then there's going to be this related graph, which, well, these numbers are going to get a lot bigger. So we'll maybe draw a new one. So let's just start with this here. So we know that for this graph, maybe it goes, if we go all the way up to 8, then x can go all the way up to plus or minus 2. Maybe, sure, we could go farther, but as you can see, these numbers are getting very small, and it's like you keep dividing by e as you go to the left, because you keep, that's the opposite of going to the right. When you go to the right, you're multiplying by e. So you have small number, any number to the 0th power is 1. And then as you go to the right, well, you have 1, but then 1 times e is 2.7 something, which is pretty big. And then you multiply by e again, you multiply by another 2.718 something. And now all of a sudden you're up to 7.3. And that's kind of a big deal. So it looks something kind of like this. So let's talk about what the transformations do. So dividing by 0.04 is going to be the same thing as times 25. So we're going to have these new x's. We're going to have, so for this new function here, y is equal to 200 e to the 0 or 0.04x. It's kind of like if this function, we're multiplying the x's by 0.04, so it slows everything down. We need big x's plugged into this x before we end up taking e to the old powers. So now we've got, for the new function, x is this, and then y is 200 e to the 0.4x plus 50. So the y's, we take the old y's, which now correspond to these new x's, but we take the old y's, where's the green? So the green is, we have the function, and then after we apply the function, we multiply by 200. Instead of, here's before we apply the function, that divides the x's by 0.04, but after we apply the exponential function, we multiply by y by 200. That's like our second step. Our first step was the, what did we do with, when we multiplied the x by that, and then the very last step is add 50 to y. So this will be kind of, so that's what we do. We multiply by 200, but then we also add 50. And these numbers, yeah, the decimal decimals. I'm gonna need a calculator for the other ones. So this one I multiply by 200. I get 544. Basically 594 after I add that last 50. So times 200 plus 50. Times 200 is, and then plus 50. So 0.37 times 200 is 74, and then plus 50. And then finally 0.14 times 200 plus 50 is that right there, 78. So if the original one was kind of like this, the new one, it takes a lot longer because it's kind of like X has to go all the way out to 50 before all the cool stuff happens. But eventually we get get that good old exponential. Because this point right here now corresponds to well, let's see, this lowest one is 250, but it goes all the way up to 1500. So if I go by 500s, one, two, three, four, five. So it starts out when x is 0. This point right here becomes this point right here. So that's the first one, and then when x is 25, we get 594, which is somewhere right about here. 1528 is like a little bit higher up here, just a little bit above this hash mark. And then sure, 124 is like down here. 78, well, it's not approaching 0, now it's just approaching 50, which is like, so the horizontal, here we have y equals 0 as the horizontal asymptote. Now it's hard to see because the constant that we added is kind of small, but here's y is equal to 0 is the x-axis, but here we have remember, the horizontal asymptote gets transformed along with everybody else. So the new horizontal asymptote is a constant that's added on, outside of everything. So you take e of constant times x, you multiply by another constant, then you add a constant at the end. That constant at the very end is the horizontal asymptote. And it looks like that. And that's roughly what it looks like. So E is the most annoying one. You always get decimals, except for the one of 0, 1 at the origin. Everything else is just these kind of annoying numbers, and there's nothing you can do about it. So let's just practice a couple more with nicer numbers. So it's very specific strategy. We want to memorize kind of roughly how just the basic ones behave, and then we want to use that to understand the new one. So f of x might be something like this. So let's talk about the base of the exponential function. This one, we don't have like 2 to the x, we don't have 3 to the x, we have a very small number to the x. Well, we want to have positive bases because weird things happen. Weird things happen if you have a negative base, and if the base is 1, then 1 to any power is just 1. So those are the two things that we require for the exponential function. But if base is just have this in mind. B to the x looks like this. Well, here's 1 when x is equal to 0. You get y is equal to 1. You get this, and then exponential b is less than 1 but still bigger than 0. You get exponential decay, which is same pattern, only reversed. And if you plug in a few numbers, unless the base is really, really close to 1, usually pretty rapidly you start to see this, that like if it's 1/2 to the x, so you have 1, then you have 1/2, then 1/4, and then you go backwards in time. It's, it's completely the opposite. 1/2 to the -1 is 2, and it's exponential growth going backwards in time, but going forwards in time, this one's decay. So these are you want to have that. You want to have this picture in mind, but you just want to start plugging in numbers here, basically. So what do we get? Well, let's actually go ahead and add. Let's make this function have 2 transformations involved. So it's, for this one, it's an exponential decay, but the base is 1/5, which is a little bit nicer. So let's just do the basic one in black. If I go backwards in time by 1, yeah, okay. I would like to go up to like 625, I guess. 3, 4, 5, 6, 700 would be up here. So that's not 1, that's supposed to be 100. All right. Yeah, let's just start with the basic one. Yeah, let's just do the basic one first. Let me not get ahead of myself. Maybe I'll only do this much. So if I plug in, so just the exponential part, which is 1/5 to the x with no modifiers. There's 1, 2, 3, 4, 5. One-fifth to the first is just 1/5, and then it's 1/25. Very rapidly gets very small, but then 1/5 to the -1 is way up here. a lot happens very, very quickly. Okay, so yeah, let's put a little table out here, and then we'll see. Basically, need room for a table. So here I didn't do anything with the x's. So here the x's are still the same, but the y's, I multiplied the output by something, and then I added something to get the final result. So I multiply by 125, then I add 25. So here's the output. I multiply by 125, I add 25. If I multiply this by 125 and then add 25, I only get this. And then this. And actually, the original graph, when x goes to infinity, the output approaches 0. Okay, so the output approaches 125 times 0, but then plus another 25. So, but anyways, the whole point is the horizontal asymptote is here. That should maybe be one of the first things that we consider. And what do we have? We have, here's 1, 2, 3, 4, 5, 6, 7. So that's 700. Okay, then that's, you know, if this is 100 each, so 175, when x is 0. -1 puts us up here at 650. 1 x equals 1 puts us over here at 50. Two puts us down here at 30, and well, here it's that's the trouble with exponential graphs. You get very big numbers if you follow the exponential function too far in either in one of the two directions. But you do want to keep in mind that your new horizontal asymptote is shifted up by exactly whatever the added constant is on the outside at the very end there. So I'm not looking for too much more than that. If you have these two tables, trying to fit both of them into the same graph, well, if I multiply by a big number, then they don't really want to fit on the same scale, so that can get pretty weird. I think using tables to indicate what transformations you're using will be very, very clear. I'll be able to follow it very easily. So just whatever you do, try to be as clear as possible about how your transformation is working. And quite often, like if it's dollar amounts, then yeah, quite often you're multiplying by thousands of dollars, and then the amount of interest might, you might only gain like 10 or 20% over a time period, and that's a big deal. But it's but the orders of magnitude compared to the original exponential function will be drastically altered, but then using a table is like really how you see that, you know, these x's and y's are corresponding to each other. But that's kind of it. It's a little bit tedious, a little bit annoying, but it's also kind of just kind of plugging in numbers. It's a lot of it old stuff, but the main point of this is that because of transformations, there's only so many things that can possibly happen. Also keep in mind that if this thing is negative, if you multiply by a negative, you would get, you would get something like that instead. So you want to pay attention to that. But if you do all the steps that you were doing with transformations back when we did 2.5, it's exactly the same thing, but now's a good time to brush up on it is all.